already started telling us exactly where you're attending from. So if all the other attendees could kindly just let us know where they're attending from. Welcome to today's webinar. My name is Kumo, and I will be the moderator for today's webinar that's going to be presented by our so ever insightful Professor Kalam. And I would just like to let you know that I'm a course advisor for ECT, which is our sister institution based in the UK. Thank you all for attending today. And I would like to turn your attention to the following slide. Could you kindly just switch off any sort of notifications you may have? This is just to minimize the disruptions that may come up during the presentation. And I would also like you guys to make use of the Q&A function, which you'll see on the top. But if you do not have the new Teams, then feel free to type in your questions into the chat box, okay? So you will receive a copy of the slides and the video recording for this presentation. So it will be sent to your email within 2 days from today. And then the certificate of attendance will also be sent to you in your email, provided you complete the survey from the QR code or the link that we will provide closer to the end of the presentation. And that will be sent to your email within 4 business days. So just check your junk mail, spam mail. Alternatively, it could be in the promotions folder of your email. So I would just like to let you guys know a little bit about EIT for those of you that's the first time attending our webinars. And what makes EIT unique or special, should I say, is the fact that we are an engineering specialist that offers industry-orientated programs with a world-class Australia accredited education. So this is all made possible by our industry experienced lecturers. For example, we've got Professor Kalam here. He's one of the ones that make this possible. And we also offer a unique delivery model. Okay, so in terms of our institutions, we've got 2 other institutions apart from EIT, which offer higher education qualifications. So ECT is located in the UK, so it offers UK qualifications, and ECST is located in South Africa. And at the moment, we are offering one course, which is the Bachelor of Engineering Technology in Electrical Engineering. So it does have a second number, and we will be rolling out other programs as time goes. So that's just a little bit about our other institutions. And just so you guys are aware, they all have different websites. So in order for you to check the relevant qualification that you desire, you can always go onto the websites, which are on the screen. So like I've mentioned, one is in South Africa, EIT in Australia, and ECT in the UK. And for today's event conduct, I would just like you guys to follow the instructions that I give so we can have a smooth running presentation today. So today's webinar will be presented by Professor Kalam, and the topic for today is the vanishing fault. Why did the circuit breaker trip with no recorded fault? I wonder why. But Professor Kalam is the one that will let us know. And Dr. Kalam, if you don't mind, could you please kindly take control and start with the presentation?
Right, give me 1 minute, please.
Sure, no worries, no worries.
Can you hear me, Kumo? And can you see my slides move? It's slide number 9,
Yes,
8,
sir,
9.
correct. Yes, and I can hear you
It's moving,
perfectly
right?
fine.
Thank you very much. Thank you very much, Kumo. And you've started very well. I think this is one of the best start we have had. And thank you very much for your support and your wonderful start and your moderating this particular session. We're definitely blessed with your company. Thank you.
Thank you,
Now,
sir.
coming back to the presentation. Uh, First of all, let me explain to you what I'm trying to do. This is not going to be an ordinary lecture. Remember that. This is not going to be an ordinary lecture. And it's so nice to see such a huge number of people coming. In the past, I've had this, I've been going with this from last month. In January, we had it, and February, we are having it. Every month, we're having 2 of these on the second and third Thursdays. Today is the first one of the February one, and then there'll be a next one on next Thursday. But just wanted to tell you that these are just mysteries, and I don't think there is a textbook solution. I do not believe that there is going to be a textbook solution. That's number one. Number two, I'm not going to tell you all the details of theory and mathematics or no, nothing. This is purely storytelling. I'll be giving you stories. It's just a lullaby baby toy, making, I don't want to make you sleep, but in the same token, I want you to understand that in engineering, many things happen where there is no reason. And these are the unusual situations that you do not expect to have. Like when you have a recorded fault, the circuit breaker should trip. If the circuit breaker trips, then the fault is known. Yeah, in this case, and I'm giving you live example, right? In this case, the circuit breaker tripped. There was no recorded fault. And this was the vanishing fault. Why did this happen? So here, what we are going to do, listen to this very carefully. I'm not going to talk only of engineering. I'm going to talk about forensic science. Then I'm going to talk about protection coordination. And then I'm going to talk about nonlinear system behavior. Therefore, first thing I want to mention to all of you, welcome, my friends. Welcome. There are 81 people attending today. Welcome to all 81 of you. Today, we are not going to look at a textbook faults. We are looking at the anomalies that keep asset managers awake at night. Situation where the data doesn't immediately match the outcome. The data is different and the outcome is different. And that is the interesting part. A bit about myself, because although most of you know me, if you don't know me, here it is. I am working as an emeritus professor at EIT along with Victoria University. I have my lot of other positions I hold simultaneously. Don't want to talk about it, but the important one is I have the editor in chief of Australian Journal of Electrical and Electronic Engineering. I published over 600 papers, 29 books, and about 53 research graduates, research PhDs, and master's students have graduated under my supervision. And currently, I have about 10 uh, research students who are working in various doctoral programs. Now, I have my own consultancy company. My PhD is from England in Bath, and my master's from United States in Oklahoma. And I did my initial studies in India. I'm a professional member of most of the Electrical Engineering Society. I'm a die-hard electrical engineering person, and I think I'm still learning electrical engineering. So I'm trying to become an expert in electrical engineering, and that's about me. And as I said, today we have certain agenda, and I want to follow that. And the agenda is already there, right? I don't want to go through it, but this is what the seventh thing I'm going to do today. Now, the first question that comes in everyone's mind: why study these mysteries? Why? Why am I going to do this? The reason is very simple. My friend, in reality, it is not a textbook solution that is there. When you're working in the field, you will find what you have learned in the textbook may not be exactly the same what you will see in reality. In real time solution, it's quite different. And data is often incomplete or misleading. Okay, you never know what is right, what is wrong, and you as engineers have to decide. You have to decide all the facts, and you have to know those facts before the occurrence, before the abnormalities occur. And here, three things are very important: safety, reliability, and cost. Remember, all those three things can cost you not only your job, it might cost closure of your industry. So it's very important that you realize that. So you, as postgraduate engineers, you must remember you are going to transition from formula-based thinking to judgment-based thinking. Listen to me carefully. No more formula-based. You are judgment-based engineers. This mysteries that I'm going to talk about is going to sharpen your diagnostic skills and professional intuition. And there is no right answer and there is no wrong answer. So, my friends, my friends, you as an engineer, I'm asking you to become a detective. You become Sherlock Holmes, right? I want you to become that. I want you to see the gaps between theoretical model that you've always done with the help of all these softwares that you know about, and talk about reality in the field. I'm going to talk about the recorders, and the recorders that I'm going to talk about are the events recorder, or something which captures the waveform like ComTrade. So remember, the event recorders, those who don't know that, are a sequence of event recording. And that keeps on going on in the substation. And these recording and waveform are always captured. So you as engineer who's sitting in a CVD can get hold of that and ask that to be said so you can do the analysis later on. And these waveforms are very important, my friends. I will show you the waveform. They are crucial for analyzing power system events and ensuring that you have got your system which is very reliable. So, as far as you are concerned, my friends, as far as you are concerned, okay, this is the mystery that's going to happen. And I'm going to show you how you're going to do the observation. What are the hypotheses? How are the simulations? And how is the verification to be done? You as postgraduates are so fixed and focused on steady state situation. Some of you know how to do transient modeling too. But many times in abnormal situations, my friend, that missing data which is there is more important than the recorded cases. And that missing data can give you the clues. So here, you now are no longer Tom, Dick, and Harry, but you're Sherlock Holmes. So, what is the objectives I have in mind? Very simple. Okay. And I do not want you to memorize. I do not want you to mug up by heart. I just want you to develop a methodological, investigative mindset. That is my aim, my friends. My aim is to develop in you a methodical, investigative mindset. That's all I want you to do. And in this case, I want you to understand the unexplained breaker trips. Why did the breaker trip when there was no recorded fault? I want you to analyze the logic of the relays and any blind spot that they might have been there. I want you to see and investigate the DC and the auxiliary system. I want you to act like a professional engineer and professionally do the diagnostics. That's what I want you to do. So, my friend, what I want to tell you is that I am going to use mysteries in practical electrical engineering because that's all I know. Why did the breaker trip? Why did the circuit breaker trip? Because in normal circumstances, you have read in the textbook, there are recorded faults and the breaker trip. Isn't that right? So I want to set you the scene. And that's where I'm trying to make it very interesting by making you Sherlock Holmes. You are the detective. This is a story. And everything that you will see appears normally after the trip. So my objectives are very clear. I want you to see actual cases. I want you to see the structure. And I want you to understand why transient faults matter. Transient fault is for a very short period of time. Why does it matter? 90% of the time the system is under steady state. Is that 10% of the time that you have transient and all the problems occur at that time? And a simple example, I've taken an 11 kV industrial feeder and that tripped unexpectedly. There was no protection relay fault recorded. So there was no recording of the relay operating. SCADA logs are normal. Those who don't know what SCADA is, supervisory control and data acquisition. They're normal before and after. And system restored without issue. That was the incident. So therefore, let me set the scene. Let me set the scene. You have a rural feeder. You have all the circuit breaker. There are different types and ratings. And there are environmental conditions. Look, environment plays a very important role. Okay. Now, someone might ask, why is this a mystery? Why is this a mystery? My first thing is that it was a random breaker trips. It should not have tripped, but it did trip. There was no short circuit detected because fault was not recorded. And when you, as an engineer, went to the substation, talked to the operator, they could not replicate the issue. Here, you, as an engineer who have done studies at various universities and higher education institutions, know In real protection system, it is not like that. The breaker trips, short circuit is detected, and operators always can replicate the issue. That's what you've learned. But that did not happen. Then you as a student can ask me, Prof, if nothing is wrong, why did the breaker trip? Why did the breaker open? This is what I want to inculcate in you: curiosity and skepticism. My friends, breakers do not trip randomly. No recorded overcurrent or on earth or earth fault. No visible equipment damage, yet the trip was real and disruptive. My friends, this is a very complex case. This is a very complex case. And therefore, the mystery is becoming more interesting. So what I do, I go back and look at all the things that I have learned in my bachelor's degree and master's degree, and you're doing in your PhD at the moment. Look at all the books, etc. Look at all the research material that has been published in IEEE, IET, MDPI, whatever it is, whichever journals you can think of. But you would first think that the relay malfunctioned. Then you would think there was a failure in the SCADA. And then you will think that the operator was in error. All that is wrong. All that is wrong. You have jumped to the conclusion, and the true cause you have mastered. Don't blame others. Do not blame the operator. Do not blame the instrument. Believe me, instrument is always right. So you've jumped to the conclusion, not before finding what is the actual cause. So my friends, let me go back and do a bit of protection. Let me go and do a bit of protection. And remember, I have got this stuff. I have got this stuff, right? And that stuff is the relay. And that stuff that I have is relay. What does that relay see? It sees the secondary current that is coming from the transducers. It sees the voltage transformers. It sees the secondary voltage. And then it does all these logic and does all the sampling. And then based on the threshold condition, makes a decision and sends a signal to the circuit breaker to operate. That's all it does. My friends, relay do not trip. When you read the textbook, you understand the relay does not trip. Relay does a signal to the circuit breaker and the circuit breaker trips. So remember, relays only see, and it is a representation of a reality. That is not a reality. The reality is done by the circuit breaker. So the relay will send the signal for the circuit breaker to trip. If there is no signal, the circuit breaker will not trip. If there's abnormality, the circuit breaker will trip. Now, if I can see the category of vanishing fault, and I'm going to the taxonomy that will guide my investigation. There are various type of faults. One could be a hanging wall block type, the fault, normal fault. There could be reverse fault. There could be lateral fault. There could be a normal fault with rotational movement. There could be so many different types. I've only chosen 5 of them. But most of them, when the abnormality occurs, the fault is transitory in nature. That means for a very short period of time. And many times, these are a high impedance fault, and it is intermittent in nature and is triggered by non-electrical condition, and the power system protection artifacts comes into operation. So with that in mind, let me go dig a bit deeper. Let me dig a bit deeper and make this mystery a bit more interesting by bringing the theory that I have learned and try and see what it is. What type of faults are transitory faults? How it is induced? Okay, remember, in the past, it was always lightning strikes. When lightning strikes, there's over voltages, right? And transient fault. For a very short period of time, very heavy voltage comes in, and there's like that type of fault has been minimized because there are surge arresters all around. Exactly in the same manner, there could be switching surges, which is a series type of fault instead of the shunt type of fault. And remember, the switching surges are now more of a problem than the lightning surges. And sometimes insulation breaks down. Many times, these transient faults, my friends, remember, I told you for a very short period of time, it will clear itself. The logging system might not open at all and there might not be any response. Many times it happens that. I've seen it many times. So it is not something that every time this happens, we will have a system which will be responded to. So the question is that why did the transient fault leave no trace? And that's why I want to discuss with you what we call sampling rates and protection opening time. Look at this curve that I have got. This is the different time at which the protection operates. And the time duration and the load. It when the load current is high, it operates very quickly, maybe instantaneously. So if the fault duration is less than the relay event window, then you will have the peak current which is clipped by the CT saturation. And at that time, my event recorder is not triggered. Let me go a bit further. Let me go a bit further and come back a bit more and look at a condition which is defined as high impedance fault. A high impedance fault, my friends, occurs when an energized conductor makes contact with a high resistance non-metallic surface, such as dry soil, pavement, grass, or a tree branch. And this results in a fault current which is very, very low and not easily detected by a standard overcurrent protection. So your overcurrent protection, which is there, can't see it. The current is so low. So that is what is the definition. And the impact is that your overcurrent has not operated. The challenge is therefore is in detection. And that depends on the various load conditions that is there in the system. Now, these faults that I'm talking about, especially the high impedance fault, they have got certain characteristics, but they do cause instability and they cause issues like public safety, fire hazard, equipment damage, operational challenge. Look at this. The equipment has been damaged. And that is due to low fault current, my friend. There's arcing over there, continuously arcing, and that coil has been destroyed. And that is unstable arcing behavior occurs, and this is invisible to the protection. It could be due to loose connection, it could be due to contamination, it could be due to carbonization. So, my friends, let us now go and see the saturation effect. And you know that if the current does not decay after a trip command, the breaker failure logic initiates backup tripping. If the primary tripping fails, the backup comes. And that is where you have what we call breaker failure protection. They call it, the device number is 50BF. And they act like a critical backup. And they are the one who initiate a trip of surrounding breakers if the primary breaker fails. That means it has not interrupted when the fault current within a set period of time, which could be within 6 to 12 cycles, after the trip signal has been issued. It triggers when a trip command is issued. That means the breaker failure one has been issued. And after a delay of some time, when the current persists. So this is a high DC offset during fault. The core has reached the saturation limits of the secondary current, and relay sees this as a reduced or distorted signal. Look at the two signals, the primary signal and the secondary signal that I have shown. Now, my friends, in, in our study, in all the breaker protection systems that I have done, I find that many trips are initiated locally by the breaker, not the relay itself. Remember, I told you, relay is just the system ordering. It's just an intelligent device. Relay is just an intelligent device like your brain. Your hand and foot keeps on mating. Brain sends the signal for the hand and foot to move. My brain is sending signal to show you, and I'm using my hand, my foot, or whatever I'm using. But all the intelligence is done through here. So the relay is not doing anything. It's just doing the intelligence, doing the sampling, etc. So the breaker self-protection functions are using SS6 type or the vacuum pressure monitoring. You can use spring charging supervision. You can use internal pressure monitoring or the anti-pumping logic. So there are many such things which can happen. Okay. And when that happens, my friends, you are going to have mechanical and auxiliary causes. And mechanical could be your wiring could be loose. Due to vibration, there could be contact bounce, and the auxiliary relay might chatter. I want to stress here, you as an electrical engineer now have to think mechanically. You're no longer an electrical engineer. You now have to think mechanically. So there, I started with forensic, I went to electrical, now I'm going to mechanical. And that is the beauty of engineering, my friend. There's so much synergy. So my friends, let me do my detective work now. And let me see what are the clues I have. The first clue I have is to look at my log, which is indicating the momentary disturbance. And then look at the protection, because the protection did not latch as permanent fault. Look at vegetation, proximity to the line. Now, look at that. Now I'm going to vegetation, so I'm going to environmental conditions. Look at the vegetation, my friend. So your job has been multiplied. So here, when you're becoming a Sherlock Holmes, you're going to start investigation. And I'm going to talk purely on engineering investigation because for us, engineering judgment is crucial and is critical. So you have looked at the transient fault concentration. You have looked at the overall potential of arcing. You have looked at wind-induced conductor movement. You have looked at all these things, my friends. You have looked at all these things. And then you want to look at the issues of coordination of protection, which is protection coordination issues. And there, I want to see What is the misconduct coordination risk that I have got? What are the short tripping times during transiency I have? And if there is any oversensitivity of the relay settings. My friends, this is when this is when I look at my overcurrent protection. This is when I look at my overcurrent protection. And I find that in my overcurrent protection, I have got this condition. And look at that. That is, again, device number is 50/51. Okay. And I'm going to look at this particular condition as the ANSI 50, which is an instantaneous overcurrent protection, and ANSI 51, which is time overcurrent protection. So um, the instantaneous and time overcurrent protection may not operate, for short duration. The combined logic may do it. The combined logic may do it. Remember, I told you very short duration, transient. Okay. So let us try and think about the combined logic. Okay. Where in this case, what I'm doing, my friends, what I'm doing is I'm using um, I'm using this combined logic in which I have now got I have got the one which includes the earth. That is why that N is there, the neutral conductor. Okay. And if you look at that combined logic, these two functions are integrated into a single protective relay. Okay. And they offer a comprehensive solution. The 51 part does all the handling of overload. The 50 element acts like an instantaneous safety net if there is a short condition. And the combination gives you that flexibility and robust operation in protection, addressing both the low magnitude. Remember, I told you the current is of very low magnitude, and my overcurrent protection could not work. And if it is of long duration fault where there is overload and high magnitude, short duration fault where there is a short circuit. So all three conditions are combined together. And this is what I've shown you, the one with 50N and 51N, which is the neutral one, or some people call it 50G or 51G, which is the ground one. They apply specifically to detect ground faults, my friends. So then what I do, then what I do is look at my breaker failure protection logic. So the current has not decayed. The trip command has gone, but current has not decayed. Breaker failure logic initiates the backup. You remember I told you the primary has failed, the backup has come in. This is where that 50 BF that I'm showing you, the breaker failure protection comes in. And that acts like a critical backup. It initiates the trip of surrounding breakers if the primary breaker fails. That is, remember I told you 6 to 12 cycle, the primary breaker should have operated. It sends the signal for the backup to come. It triggers a trip command, which is initiated by BF1, by this breaker failure, BF1, right? And after a delay, the current persists. Now, let me look at the role of DC current, of the DC control system. Remember, my friends, that protection depends on the integrity of the DC. Because if you have an unintended leakage or wiring faults, this can definitely energize the trip coil without any primary fault. The DC trips because it is using a DC supply, protective relay contacts, and a trip coil, which is initiating the breaker opening. So the breaker is open. The fault has not been recorded, right? This is unintended, spurious trip due to the degradation of the insulation. I showed you how the insulation was damaged. It could be due to moisture, it could be due to wiring faults, it could be due to some protective contacts. These issues can be mitigated by monitoring for ground faults and ensuring that you have got adequate cable insulation. So this DC fault is causing my fault strip. And many times, because you have not studied in your textbook, you will overlook this in your investigation. Okay, so let us now go to look at the DC trip circuit. Remember, I told you that that's where the DC trip circuit. Look at that. That's your DC, and the trip coil is there, and the circuit breaker is stripped because that's what that is the unintended leakage or the wiring faults, and that's energized by that trip circuit, and there is no primary fault at that point. So then my next stage is to look at the environment. Environment plays a very important part, my friend. And remember, non-electrical causes can trigger trips. You'll be surprised. Non-electric, it could be moisture ingression, could be extreme temperature, it could be dust and contamination. I remember very clearly when we had the bushfire, last bushfire in Victoria, and I was part of the Royal Commission. And we found, and I did the test in my own backyard, and the fault was in one place, and my apple tree was about 5 meters away, and the apple tree burned down. Moisture condition. Temperature was extreme on that day. There was all sorts of dust and contamination. Look at that. It's damaged. It's all damaged. Okay. Then let me look at one very interesting thing. Whether you like it or not, engineers are a part of the system, right? And engineers are human. You'll be surprised. Human makes most of the mistake. It's not the machine. Maintenance induce latent faults, but the incorrect setting, updates, etc., could be all human factor, which could lead to the test link, which is left installed, right, and it's temporary, but that has caused the fault. So we as engineers are part of the system. I'm just trying to stress that we are part of the system. So my friends, if I look carefully, if I look carefully, then I find, if I look carefully, then I look at the event recorders. I told you I will show you at the event recorder. Okay? And this is where I want you to think critically, because you want to read the data. There's no point having all these data over there when you don't read it. If there is no record, there is no event. And then later on, you can sit in your office in CBD and do the resolution and triggering. And look at the log, look at this log, and there is where you get the interpretation. Look at this, and you will see the interpretation over there. My friends, you have to do an investigation which is very structured. Use the structured approach. Do not destroy evidence. Preserve them. Review all your settings and logics. Inspect your primary equipment. Test your DC and auxiliary circuit. You have to have a discipline and keep your documentation intact. So you need to ask the right question. You need to ask. There's no point if you're not asking the right question. You need to ask your operator, what changed recently? Was there any weather involved? Was there a calamity? Was there a typhoon? Was there a cyclone? Was there a very hot condition? Did anything almost fail or only that particular symptom fail? So please ask the right question if you want an answer. So now look at the resolution of the case. It was definitely some sort of moisture in that marshalling kiosk. Environment was the one which caused the mystery trip. It caused the DC trip circuit leakage, and there was a momentarily uninterpreted trip. So, environment, friends, you can see that look at my initial investigation that I started. No fault was recorded. There was no primary fault current. Relay never asserted, but still the trip was initiated. There was no fault. There was relay never did anything. Relay never did the signal, but because of the moisture condition that is there, that did happen. So, my friends, you as the early career engineers and students doing your higher degrees have to do, please broaden your thinking. Instead of being narrow, broaden it up. Look at the importance of DC system. Look at much beyond what you say, environmental condition. Look at human machine interface, the HMR. Now, in real world, my friend, real world, my friend, this is what has happened. There is something unexplained. And this a condition that I showed you, the unexplanation was on the real world condition when there was a nuisance trip. The customer would lose confidence in you. If you lose the customer, you're going to lose money. And you'll come under the scrutiny of the regulator. So, my friends, you have to be careful. You have to be careful because your your engineering judgment is under uncertainty. And you cannot make decision if you do not have complete data. Your decision without complete data is very risky. You have to balance the risk and cost. You must know when to escalate the issue. If you can't do it, you have to get someone else to do it. So I want you to understand this. I would have normally asked you questions at this stage, but looking at the time, I'm really at the end. I would ask you this question, and I would like you to think about it. Would you reclose immediately? What evidence would you demand? When it is justifiable to ask for replacement. Look, if you want to ask for just replacement, do you change the circuit breaker? Do you know how much a circuit breaker costs? It might cost you at least $20 to $50,000. Who's going to spend that just because of your whim? No. So you have to decide when is the appropriate time to change it. So my lesson today, my friends, are as follows, and this is my key takeaway. Not all trips are electrical fault. There are blind spots. You, as a good engineer, has to be a good Sherlock Holmes, not a failed Sherlock Holmes. You have to be a good one, and you have to have a mindset where you can solve these type of mysteries. And in fact, if I was you, I would go deeper into the investigation. Look at load variation, which is influencing the sensitivity. Look at the local weather impact. Look at soil condition. Look at environmental conditions. And then I could have said that I have solved the problem. I know what is the root cause. My root cause was that there was an arc which was due to vegetation during the wind, transient and self-clearing nature, okay, protection activated before clearing. And the missed factors that I had, and the missed factors that I had are as follows. There was no transient monitoring devices in place. Assumption was that it was always a permanent fault. Vegetation was inadequate, so you did not do any clearance over there in your planning state. So you as professional engineers have to look at the inside, look at the SCADA data, find what the high-speed fault recorders say, and do the routine environmental risk assessment. So when you're doing this, my friends, try and look at it as a protection engineer or an electrical engineer. You should have a professional insight into the matter. And the professional insight, what you would do is to review your relay coordination, look at the transient scenario, look at the vegetation and environmental inspection. As a regulatory issues, look at the Australian standard or New Zealand standard 3000 requirement and look at IEC transient protection standards. And what are the lessons that I have learned from this? You and me both have learned from this. Transient fault can cause breaker trips without permanent fault. The lesson I learned, data analysis is crucial. The lesson I've learned, coordination saves operational cost. Think beyond fault current. Respect your auxiliary system. Investigate systematically. And in conclusion, what I want to say is that you understand properly your transient phenomena. And if you understand that, you cannot do misdiagnosis. You will be a proactive engineer. Your downtime will reduce, and absence of evidence is not evidence of absence. Remember that absence of evidence is not evidence of absence. So, this is my philosophical reflection about engineering practice. Okay. So, with that, I have completed my presentation for today, and I'm open to any question and answer. And I leave it to Kumo to say whatever he wants to say now. Kumo, it's all yours, Kumo. You can take back
Thank
the.
you, Prof. That was a really great presentation. I'm sure attendees can agree to that. So if we do have any questions, we've got about 7 minutes before we can wrap up the session. So if you guys do have questions, you can post them in the Q&A box or in the chat if you would prefer to post your questions there. And Job Kwame, we will share the slides. As I've mentioned earlier on, that the slides will be shared to you guys and the video recording of this within 2 business days. So just monitor your emails. If it's not in your inbox, kindly check your spam junk or alternatively your promotions folder, because sometimes they do end up there. So I'll just give it another minute or so, and if there are no questions, we'll wrap it up. But thank you all for attending this webinar today. I'm sure you guys have learned something, if not a lot, as myself I have. And once again, thank you, Prof.
Thank you very much. There was a very nice question from Krish Prasad. Krish Prasad says, can partial discharge also cause tripping? Absolutely. Absolutely. It does. Because, in fact, the whole insulation might be damaged. And then there is uh, it's all my insight. I'm sorry, my knowledge is very limited. Okay, I'm not as good as you people are, but I try to share my limited knowledge to all of you. But I'm glad that you appreciate whatever I'm telling you.
So I have included the certificate of attendance link. So there's a questionnaire that you'll first need to complete and then submit the profile, or rather the form, and then it will generate that information to us, and then we will be able to send you guys your certificate of attendance. So if you don't do that, unfortunately, you'll not be able to receive the certificate of attendance for today's webinar. I hope that makes sense. Which forms are these? It's for the certificate of attendance. So if you just fill out the form, and then you can submit it, and that will give us the go ahead to actually generate the certificate of attendance for you and send it to your email. Okay, I would just like to, before we wrap up, I'd just like to say thank you, as I already have. And secondly, to just highlight the upcoming courses for our different institutions. As I've mentioned earlier on, there are 3 different entities: EIT, obviously Australia; ECT, UK qualifications; ECST, South African. So these are the courses, but you could just go to any one of the websites that may interest you. Okay. So we also are running a competition, and all you'll need to do is take a picture highlighting something to do with engineering, and then it will close on the 31st of March, and there's 4 prizes to be won, and the top prize is $1,000 cash prize. So all you need to do is take a picture, tag us on our socials, that being Instagram, LinkedIn, Facebook, or TikTok. So the choice is yours there. If is there anything else?
Yes, I just wanted to tell that next Thursday, same time, I'm having another session, another very interesting case. The case of a transformer that hummed at midnight. I could not understand. Why was it humming at midnight? As if it was talking in midnight. This is a mystery. And let us talk about this next time.
Yeah,
And
sure. Please join. Go ahead. Sorry,
with
Prof.
that, I'm so sorry. But bye for today. Keep healthy and stay calm. And keep in touch with these mysteries. It'll make you sleep better. Remember, you are the Sherlock Holmes. I am the dragon. We are all part of the system.
Thank you so
Bye bye
much,
for
Prof.
now.
Love that. So you guys can check out the next session on our websites. Feel free to register for that and join us for that. Thank you and have a good day. Bye.
And thank you very much, Kumo. You were a great moderator. Thanks a lot. Bye
Thank you,
bye.
sir.
Not only great, but also beautiful and handsome.
Bye-bye. Bye.
Bye.
Thank you. You too, sir.